Hi, I'm Zhe Jun. In this video, I will present our paper, a multiplicative value function for safe and efficient reinforcement learning. This is a joint work by Nick Buehrer, Zhejun Zhang, Alexander Liniger, Fischer Yu, and Luc van Gu from the Computer Vision Lab of ETH Zurich. We consider safety as constraint satisfaction, for example, collision avoidance. In Figure A, we see a simple navigation environment where the goal is the circle at the center and the obstacles are the gray rectangles. Figure B is the ground truth value function of an LQR policy. As we can see, there are sharp boundaries in the value landscape. This is because to enforce safe behavior, standard RL methods would give a large penalty to the collision with obstacles. These sharp discontinuities lead to poor training stability and sample efficiency, because they are hard to be approximated by a neural network, as we can see in Figure C. To address this problem, we propose a multiplicative value function. We facilitate the learning task by splitting the responsibilities. Specifically, we use a safety critic to estimate the probability of constraint violation and multiply it with the constraint-free reward critic. This effectively decomposes a difficult learning problem into two simpler problems. The safety critic learns a binary decision problem, whereas the reward critic estimates the constraint-free returns which have a smoother landscape. To avoid multiplication with negative value, the constraint-free value function is subtracted by its lower bound, and then it is multiplied by the probability of constraint satisfaction. As we can see, according to the safety critic, our multiplicative value function scales linearly between the constraint-free value and its lower bound. It is straightforward to apply this idea to policy gradient methods, such as SAC and PPO. For SAC, we formulate the multiplicative Q function in the same way as the multiplicative value function. For PPO, there are different ways to formulate the multiplicative advantage. We investigate three variations. In V1, we bootstrap the Q function. In V2, we do not bootstrap, and in V3, we bootstrap the safety critic inside the Q function of V2. In all three versions, we will replace the Q and value function with their multiplicative counterparts. Now applying our idea to SAC and PPO is as simple as replacing the regular Q function at the advantage appeared in the objective of AC and PPO by their multiplicative counterparts. We evaluate our method in 4 safety-focused RL environments and in the real world on a wheeled robot. Compared to the baselines, our methods achieve better training stability and sample efficiency. In the figure for the value loss of lunar lander, we observe the convergence of our methods is faster and the variance is smaller. Also in the table, we observe our methods have fewer constraint violations and higher rewards at the first checkpoint after 50K training iterations. At the final evaluation checkpoint after 150K iterations, our methods achieve similar performance as the Lagrangian baseline. This is expected since both are Lagrangian methods, and with enough training samples and model capacity, the regular value function can properly learn the value landscape. Qualitatively, the multiplicative value function can better represent the obstacles in the navigation tasks, as we can see in this toy example here. Compared to the Lagrangian baseline, the trajectories of our method are more directed towards the goal, and our multiplicative value function can more evenly fill up the red rectangles, which are the ground truth obstacles. After the toy example, we investigate robot navigation with a more realistic setup. Here we use a differential drive robot with 1D LiDAR data as observation. The robot is also given a vector pointing towards the goal. After training in the gazebo gym, we do zero-shot sim-to-real transfer and deploy the policy in a cluttered room. During the experiment, we dynamically block the path of the agent with boxes and our legs. Even though the agent has only encountered static objects during the training, it still shows safe behavior while interacting with us. To summarize, in this paper, we propose a multiplicative value function for safe RL. We decompose the regular value function into a constraint-free reward critic and a probabilistic safety critic. Then we combine both critics in a multiplicative way. We integrate our idea into SAC and PPO and show increased sample efficiency and learning stability. Our methods achieve superior performance in both the safety-focused RL environments and the real-world robot navigation task. As future work, we would like to investigate theoretical justification of our method. This is the end of the video. Thanks for watching.